Good afternoon. Welcome to this first live interactive session of this NPTEL course Advanced Transition Metal Organometallic Chemistry. I hope that you have by now gone over few lectures on this course, and if you have any questions or queries, I request you to submit your questions, queries, clarification in the text box given at the bottom right corner of this window, and I will take up your queries and answer them in the order in which I received them in this live session. Dear students, please send us any queries or questions that you may have by writing them down in the chat box. For the lectures that have been covered in this NPTEL course, Advanced Transition Metal Organometallic Chemistry. Good evening. Good evening. Welcome to this live interactive session for this NPTEL course. And once again, I request you to send us your queries and questions in the text box given at the bottom right corner of this window, and we will answer them in the order in which we receive them. No, no. If you have not sent the assignment, it will not. Uh, it will not uh, affect the overall evaluation. For students who have joined in late, I once again welcome all of you to this live interactive session of this NPTEL course, Advanced Transition Metal Organometallic Chemistry. And in this live session, if you have any questions or queries, you may type in the chat box and I will answer them. So please type in your questions, queries, clarification in the chat box if you have any on the portion that has been covered in the lecture. Oh, exams. Exams will be objective types. It is not going to be a subjective exam, and it will be a 100 marks exam with 100 questions. So these all will be 1 mark multiple choice questions. Half of them will have single answer correct. So of the 4 choices that you have, only one of the 4 choices will be correct. That will be half of the questions, so at least 50 of them. And the other half of the questions will can have more than one options correct. So of the 4 options, you can have more than one options that are correct. So, but there will not be any subjective type of questions. Okay, now another question is about the finding the bond order of a metal-metal bond. Now, okay, now the other question I see that how do you add this course to my qualification? I think that is as far as the NPTEL guideline. You will get some credit regarding uh, the course if you have completed them, and that can be added towards your qualification. So I request you to contact the NPTEL office as to how to credit the course towards your qualification. So now going back to the question on the metal-metal bond order. Uh, Now the the strength of the bond depends on the extent of the overlapping orbitals of two metals that get involved in forming the bond, and that a quantitative analysis of that can be obtained through density functional theory, where one can look at the filling of these bonded orbitals as well as non-bonded orbitals, filling of the electrons in these bonded and non-bonded antibonding orbitals, and one can get the bond order. Now, so for that would involve rigorous uh, quantitative theoretical computational analysis. Now, empirical approach of arriving at a metal-metal bond order is, and that is experimentally, is from X-ray single crystal diffraction studies. Now, X-ray single crystal diffraction studies would give you the distance between the two metal atoms that are bonding. Now, from the sum of the individual covalent radii, if one knows the covalent radii of a single bond of a particular atom, so when those two metal atoms come together, if the individual covalent radii are added up, so that will give some predicted single bond distance. Now, any deviation from the calculated or estimated single bond distance based on the covalent radii would also provide insight on the bond order that exists between the atoms. So if the distance is shorter, then obviously it will have a higher bond order, and if the distance is longer, then obviously it will have lower bond order. So that empirically, to some qualitatively, can be arrived at looking at the distances between the two atoms. And for a more detailed quantitative analysis of the bond order, one has to carry out detailed computational analysis, where one sees that how each of these orbitals are electronically filled. I hope I have answered your queries. So people who joined in late, again welcome to this live interactive session of this course, Advanced Transition Metal Organometallic Chemistry. And in this session we are going to be taking up questions or queries that you may have on the lectures which has been taught in the course so far, and I request you to submit your queries in the text box given in the bottom right corner of your screen, and we will answer your question in the order in which we receive them. once again welcome you all to this first live interactive session of this NPTEL course, Transition Metal, Advanced Transition Metal Organometallic Chemistry. Uh, in this interactive session, I would be answering questions or clarifications that you may have on the portion of the course that has been aired so far by NPTEL. And I request you to send in your queries and questions in the text box given at the bottom right portion of your screen, and I will answer them in the order in which I receive them. I hope you are enjoying the course. Dear students, welcome to this first live interactive session of Advanced Transition Metal Organometallic Chemistry. I hope you are enjoying this course and you have gone over the portion of the lecture which has been aired by NPTEL, and in this session I am going to be taking up questions or queries that you may have on the content which has been aired so far, and I request you to send in your queries by typing it in the chat box which is given in the bottom right corner of your screen, and I will answer them in the order in which I receive them. Dear students, request you to type in your queries and questions in this live interactive session. The purpose of this session is to interact with you and try to answer your queries that you may have on hearing this lecture. Please send in your questions, type it in the chat box if you have any. I request the students attending to ask queries and questions if you have on this course in this live interactive session. Okay, it's the effect of electron withdrawing group and electron donating group. How can you explain through back bonding? Okay. Now, there is the question that you asked. No, it can be the depends. The depends on the nature. Now, if this electron donating or electron withdrawing, if it involves resonance with a lone pair on a heteroatom, so that would call for a different explanation, as opposed to if the electron withdrawing and electron donating nature is purely an inductive effect based on electronegativity. So depending depending on the type of involvement. If there is an electron relocalization happening as a part of electron donating and electron withdrawing group present on a substituent in a metal carbon bond, then it would affect the bonding and back bonding. And we have seen this thing happen, let's say in Fischer carbene. It's a singlet carbene stabilized by ortho, so adjacent oxygen heteroatom with lone pair. So the vacant pz orbital is stabilized by the adjacent heteroatom. Okay. Whereas in the Schrock carbene, it is more of inductive effect. So a general answer to your question is it depends. It depends on what kind of electron withdrawing group and electron donating group are in place on the metal. So if it involves electron relocalization, then obviously back bonding will get affected. If also, and if it is let's say inductive effect, then also there will be a back bonding can get affected because in that case the carbene center, let's say if we have electron withdrawing group on carbon which is pulling the making the carbon more electron deficient, and that will also result in forward donation from the metal to the carbon. So depending on the nature of the group and the type of electron donation and withdrawing effects, the back bonding will get affected. In some case it may affect it significantly, and some case it is not. I hope I have answered your query on this question to your satisfaction. Okay, how can I find out oxidation state of metal? Yes, so this is very simple. Like this we have to see which are first you have to identify which are the neutral ligands and which are the anionic ligands. The ligands which will satisfy or add towards primary valency of the metal, that will determine and the oxidation state. And this has been dealt with in detail when we talk about the type of ligands. When a ligand is forming a covalent single covalent bond in its anionic form, then it is contributing towards satisfying the primary valency of the metal. And so basically when you look at a metal complex, we will have to see which ligands are accounting for the primary valency fulfillment of the metal, and from there you will calculate the oxidation state. Overall, overall the idea is the complex may be a neutral or cationic. So overall charge or charge neutrality, whatever is there, that should be maintained after fulfillment of the primary valency by the metal and the individual ligand. That is how you would calculate the oxidation state of the metal. Okay, I request the students to send in your queries and questions, and I'll be happy to answer them in this live session. So if you have any questions or queries, please type in your keyboard, in your chat box, and we'll answer them in the order in which we receive them. See how rotation when metal. Okay. See how rotation barrier changes when metal carbon bond length increases. Okay. Now think of it this. When if a let's say if a metal carbon bond is rotating. Now if the bond length decreases, then that obviously it means that it has a multiple bonded character, though it becomes shorter. Now when it becomes shorter and it has multiple bonded character, then obviously its rotational barrier will increase, because now for that metal carbon bond to rotate, now it has to break two bonds because of the multiple, one sigma bond and one said pi bond. Now think of a scenario where the metal carbon bond is very long one. So long one would imply that it is no longer a multiple bonded. It may be just a simple single bond. Now, if it is a single bond, then obviously it can rotate. So the rotational barrier will become smaller. So basically a qualitative correlation that one can arrive at is that the rotational barrier will be higher. It will be difficult to rotate if the metal carbon bond lengths are shorter, implying that it has the shortness is due to formation of metal carbon multiple bond. More than one bonds are forming, and obviously it will be difficult to break the bond for it to rotate. So the rotational barrier becomes higher. On the other hand, if the metal carbon bond length is longer, that is imply that there is no multiple bond character to the metal carbon bond, and that is more or less a single bond in nature, and hence your rotational barrier will come down. So what I just said is empirical correlation between the bond length of a metal carbon bond and its rotational barrier. I hope I have answered your question to your satisfaction. I request the students to send in your queries and questions in form of text messages in the text box given at the right bottom corner of your screen in this live interactive session, and I will answer them in the order in which I receive them. So once again, welcome to this first live interactive session of this NPTEL course, Advanced Transition Metal Organometallic Chemistry. In this interactive session, we are answering questions and queries that some of you have after listening to the lecture that has been aired in this portion of this course, and so I request you to type in your comments and queries in the text box, and I will answer them in the order in which I receive them here at the studio. Please type in your comments and queries if you have any regarding the content of the course that has been taught so far. I request the students once again to type in their queries and questions so that we can answer them in this live interactive session. This is indeed a nice opportunity in which we can interact. I can also interact with you, given the online nature of this course. It's not that possible. So I request the students to make use of this interactive session, make the most out of this interactive session by asking questions or comments or clarification that you may have on the course that you are doing. You are saying that ligand, which is sigma donor and weak pi acceptor, and sigma donor and a good pi acceptor. Okay. Now, see, from a ligand perspective, what does ligand do? So ligand will always donate. That's because it is a electron rich entity and the metal is a cation. The metal will always accept. So a good ligand will be a good sigma donor. Now, so the sigma donation is more or less an attribute which is constant for most of the ligand by and large. Almost all of the ligand that you have come across, almost all, I don't say everyone, almost all of the ligands that you come across will be known to donate electron, and that will be in a sigma fashion. The first, what is the sigma fashion of way of donating electron? That the orbitals will overlap in a head-on fashion, and that the electron density will be maximum in the internuclear distance of the bonding atom. So that's like a sigma bond, and the ligands are known to do that because they are electron rich entities. Now comes the confusing part according to you, which is pi acceptor or pi donator. So when a ligand, in addition to donating sigma in a sigma fashion, if a ligand can either additionally donate or accept electron in its pi orbital, then it will be a good pi donor or a good pi acceptor. So for example, if a ligand, after getting engaged in the sigma donation, if it has a vacant p orbital, so then that p orbital, vacant p orbital on the ligand, after donating its sigma electron through the sigma orbital, can accept an additional electron pair from the metal orbital. So in that case, if there is a vacant p orbital on the ligand, and after donating the sigma bond to the ligand, if the metal can accept electron from the, if the ligand can accept electron from the metal, so then it becomes a pi acceptor. Then it becomes a pi acceptor because along the pi bond it is accepting the electron. Now pi acceptance of a ligand accepting electron is counterintuitive to the property of a ligand. Ligand always tend to be electron rich and donate, and it is still donating. It is donating through the sigma bond, but there may be p orbital which is unfulfilled or empty, that can get some electron back from the metal. So that is like back donation happening. So it is a pi acidic ligand, pi acidic nature. Now think of a scenario where ligand can sigma donate, which is obvious, and also has a lone pair in its p orbital. So having sigma donated the sigma orbital, it may have a lone pair which is in the p orbital perpendicular to the sigma bond, and the lone pair can also be back again donated back to the metal. So then it becomes pi basic. So this pi acidic nature and the pi basic nature of the ligand depends on the availability of empty p orbital on the ligand or on the availability of a filled p orbital in the ligand. If it is empty p orbital on the ligand, then p type orbital, then it is pi acidic, and if it is filled, one pair occupied pi type orbital on the ligand, then it becomes pi basic. So this pi acidity and pi basicity happens in the pi bond, which is after the sigma bond is formation, over and above the sigma bond. So the first bond, which is the sigma bond that is formed, that always ligand gives from ligand to the metal. But after forming the sigma bond, ligand may accept electron from the metal. That is in the case when the ligand is pi acidic. In the pi orbital, it may take ligand and metal, and the ligand will have an empty p orbital. And in the case of pi basic, even on the, because the pi orbital is full, ligand will again give the pi orbital also to the metal, so it becomes pi basic. So this we have discussed in detail in the slides as well as in the Eschenbach organometallic book. I suggest you go over the content in bit more detail, and also it would help if you work out this sigma donation and pi back donation by drawing the molecular orbital that are involved in metal ligand bonding to clear your doubts. I hope I have answered your question in detail regarding the pi acidity and pi basicity of a ligand on the top of being good sigma donor. I request students to send in their questions in the text box, and I will answer them in which it is received here. I request the students to send us any questions and queries they may have. We are approaching the end of this live interactive session. So if you have any questions and comments, please put it in the text box and I will answer them. Okay, with this, if there is no further question, we come to the end of this first live interactive session of this NPTEL course, Advanced Transition Metal Organometallic Chemistry. It was indeed my pleasure to have interacted with you in this session, and I look forward to interact with you again in the next session, which will be scheduled in about 2 to 3 weeks time from now. I request you to go over the content and I hope you are enjoying this course and you are benefiting by taking this course. I wish all of you safe and a healthy stay. Please wear mask and I hope to see you in the next interactive session which will be notified to you by NPTEL. Until then, stay well and goodbye and thank you. Bye bye.